So yeah, so in the middle you can see myself, and also you can see the members of Gradient Student Club. I'm president of this organization for almost 2 years, and together with my friends we study deep learning. And currently my research with my team is focused on deep reinforcement learning. So if you know anything about reinforcement learning, so the deep learning is just reinforcement learning using deep learning methods. Also, I worked on deep learning. I worked for Intel Artificial Intelligence Product Group and Quantum Lab startup. So yeah, so today we'll talk about beautiful algorithm. We will talk about AlphaGo 0 for game of Go and its generalization to other problems Alpha 0. To those of you who don't know what is Go, it's just really complex and a really old game. It is board game. It is most famous in Asia. Alpha Zero beauty comes from its power to solve really tough problems, like playing game of Go, and also from its pureness and simplicity. Like we'll see that this is really simple idea and really simple algorithm to train really powerful policies. Alpha Zero is composed from main 3 components. We have the Monte Carlo tree search algorithm. It will be modified to use policy network and value network. Policy network is just like some guiding for the search. And value network allows us to evaluate value, so the probability of winning at each stage or at each node of the search in the tree. AlphaGo Li version of this algorithm became the first AI to beat the human grandmaster of Go in March of 2016. It is a huge achievement, as for a long time people thought that Go is the holy grail of artificial intelligence. So we were still many years before AI will beat human players. And so this is a really huge achievement, because if you ask a chess player why he chose some action, he will often tell you the strategy that he follows. They just compute some statistics of the board, and they have just some strategies to play those moves in those situations. But if you ask a Go player why he took a particular action, he will often tell you that it felt right. So the game of Go is so complex that you need a strong intuition to really master it. So to really appreciate this achievement, you need to know that the ancient game of Go has more states, valid states, than there are atoms in the known universe. So you can imagine that known universe is really large, and there are more configuration of board than there are the atoms in the known universe. And also its branching factor is almost 7 times bigger than the one of chess. So this is like from every state there are on average 7 times more options to choose action than in chess. And in October of 2017, DeepMind published new AlphaGo version. AlphaGo 0 has defeated AlphaGo 100-0. So the breakthrough is that AlphaGo 0 doesn't need a database of human expert games. So it trains solely through self-play. It doesn't need any domain knowledge, or doesn't have someone to show it how to play. And 48 days later, they published a new paper, Alpha 0. This is current state of the art. And in this paper, they show that you can move this algorithm to other problems, like playing chess or shogi. Shogi is just Chinese version of chess. And the interesting thing is that they train those algorithms 4 and 2 hours. 4 hours to beat the world champion program Stockfish in chess, and 2 hours to beat world champion Elmo program in shogi. Yeah, and also worth noting is that they trained those algorithms in Google Cloud, because DeepMind was acquired by Google some time ago, and they trained those networks in Google Cloud using 5,000 TPUs. So yeah, this is quite a compute power. They just play many games in parallel. Yeah. So yeah, today we'll talk about this algorithm. I will show you how this really works, how the learning process goes. We'll start with describing reinforcement learning. So the reinforcement learning is just a framework to formalize those kind of problems. Then we'll study policy iteration as an example of algorithm that can solve reinforcement learning problems, and also AlphaZero policy iteration is at the core of AlphaZero learning process. And at the end, we'll dive deep into AlphaZero internals, and I hope that we'll have time to show you the code and how the algorithm works, because with my friends, we re-implemented it. Yeah, and I also encourage you to ask questions anytime you don't understand something. So it will be easier. I don't know your level of knowledge. So if you don't understand something, you want me to explain something better, just raise your hand and ask question. And also there is one more thing that I hope that you won't see. You will not see. When I get too excited, I start to talk really fast. So also raise your hand and tell me that I should slow down. Okay, reinforcement learning. So yeah, so maybe some questions to this moment. Are we ready for the journey? Okay. So reinforcement learning is a way to formalize this kind of problems. We have an agent in some environment. The agent takes some action, and the environment gives the agent feedback that is composed of some state, next state of the environment, and also a reward. So if the move was good or bad. It improves. The agent needs to improve with experience. It learns by trial and error. So it just make moves and try stuff, try the different actions, see what is the feedback, and then try from this experience. Yeah, and also this framework is inspired by psychology. So you have an agent and an environment. It's like animals and humans in the world, and we just try stuff. We see how other people respond, how our environment respond, and then we learn from this information. This is an example of some environment. This is a maze-like problem. So we have an agent that lives in this grid world. The walls blocks the agent's path. States are the robot positions. So you have two coordinates, 1 to 3 and 1 to 4 in both directions. So agent receives at each time step after each action, it receives some rewards, some feedback, and it can be, for example, some living reward. So in each step, for example, it can be negative. So you have the negative living reward. So you want to act fast because just living is painful. And then there are some big rewards that came at the end. So you can see that there is some gem at the corner, and there is some lava pit. So you just don't want to go into pit and you want to pick this gem. So the goal is, of course, to maximize your sum of rewards. So because the living is painful and the reward is negative, you want to go as fast as you can to the gem. And there are two kinds of actions. There are two different types of environments. You can have deterministic grid world and stochastic grid world. In deterministic grid world, you just choose an action, and the outcome is what you expect. So you go forward. The state changes to robot that moves forward. And in the stochastic case, this can be different. So, for example, you have some probability that that robot will behave the way you chosen. But for example, there are 10% that will move left or right. So, for example, there is some wind and it can push you. So you can model those uncertainty of the environment this way. So when to use reinforcement learning? When you have data in form of trajectories, you need to make sequence of related decisions. You observe, it can be partially or noisy feedback to choice of actions, so the state and reward. And then the task requires both learning and planning. So you just experience the environment. You need to learn from this experience and also to plan next actions. And where it is used currently, those are applications to reinforcement learning and decision-making conference last year. So for example, you can see that there are robotics, video games, autonomous driving, financial trading. All of those problems can be formalized in the reinforcement learning framework. So in the framework of agent and environment, agent need to make a decision, environment give a feedback to it. So when we are talking about solving those kind of problems, the policy iteration is one of ways to do this, to solve those kind of reinforcement learning problems. First of all, we should describe what is a policy. So policy is just a map of an agent. If you have this this maze-like problem, you can see that agent have some internal map. So this is like mapping from from states, from agent positions to some actions. So this is just a policy, just what I should do in particular state. And we also need to define our goal. To make sure that I will tell you everything. I will move to my notes. So yeah, so we need to talk about some goal. What is the goal of the environment, right? So to formalize this goal, we just consider the expected return. So the expected return, like you can see, is just random variables of future rewards. So it's like we are trying to predict what are future rewards. And so random variable depends on our decisions, of course, and also on how environment works. There is also a discounted future reward. So we just discount each reward in the future about some amount. The gamma is between 0 and 1. Between 0 and 1 included. So it can be also 0 and also 1. So for example, if gamma is 0, then we only consider as a goal just next step. So what is the reward of next step? We have really short horizon. We only look for what will be we only consider the next reward, if it's good, if it's bad. And if we set gamma to 1, we have really long horizon. So we are considering some future, what will happen in the future. If we do good in the future or bad, and the gamma is just a trade-off. It's like in our life. So we need to trade off the immediate rewards, like I don't know, like eating chocolate and getting obese in the future. So this is a trade-off between short-term and long-term thinking. And this is modeled with this gamma factor. And this is also, like you can see here, the gamma is like, in the current state, the gamma is like really good. In the next step, it's worse because gamma is some discounting factor, and 2 steps ahead, it's like broken. So so it is implied that reward is better now than tomorrow. And there is an example. For example, imagine that you have a corridor. And you have just straight corridor, and you have an agent at one end, and just for example a cake at the other end. And so agent likes cakes, so it wants to go to the cake. And also horizon is infinite, so the environment doesn't stop doesn't stop before the cake is eaten. So what the agent does in two cases, without discounting and with discounting. If an agent have infinite horizon, so it can go any time to this cake, and there is no discounting, so there is no difference if I eat it now or tomorrow. So what the agent does? Yeah, it does whatever or nothing. It just stays, because what's the point of going now if tomorrow it is the same cake? So with discounting, the agent will rush for the cake, because cake tomorrow is worse than today. So this is also from mathematic point of view, the discounting, you can see that this is just a series. So when you have a continuing environment, so there is no end, then this would be an infinite sum. So with the discounting, the infinite horizon gets infinite sum, because the value is bounded. Okay. Yeah, and the point is that it's really hard to compare infinities, because how you know that some infinity is better than others. So how you would decide which policy is better if the reward is infinite? Okay, state value. If we have the concept of future reward, then we can define the state value. The state value is just the value function is just predicting how good it is to be in the state. So it just predicts so it just tries to predict the future rewards. And the fundamental property, so it's like you can see here, right? So this is a value function of state S according to some policy. This is expected value. So what we expect, if we behave this way and we know how the environment works, how we expect it to be the return, our future reward. This is just a series of those random variables. So also we can see that we can the value function has some recursive fundamental property, and this is really useful, as you will see. We can just replace the first reward with the reward we get from the reward function. So we are in some state. We take action according to our policy. And we get to some other state with our simulation, because we have access to simulation, so we know what is the next state. And we can get from reward function, we can then get some reward, and we replace it in here. And then we can the rest of the series we can replace with just value function of next state. And here's an example of two states, and you can imagine what in which state the value function will be higher. Of course, in this one, because you have like possibility to eat more those points, and in this, like you messed up. If the goals don't go the opposite ways, then you just lose. So yeah, so policy evaluation. You have this recurring form, and then what you can do is just train from. So this is the policy evaluations uses bootstrapping, and bootstrapping is just learning your estimates from other estimates. It's like the example is like you are in home and you just estimate how long it will take for you to go to the work, and you know that you are stopping for Starbucks on your way. So you estimate, for example, that there is 1 hour from your home to your work, but you get to the Starbucks and you see that it was like 30 minutes already, and you estimate that it was for 40 minutes more. So already, based on your new estimate and the knowledge that you have, you can just improve your original estimate that it's not 1 hour, it's 1 hour and 10 minutes. So why this is useful? Of course, this is useful because we can do more updates of our estimates, of our estimator before we get to the end. We can just improve our estimates, our predictions on our way, as we just interact with the environment. And also, in the case of some continuing environment, so the environment that does not have end, or the end is really long way, like for example our lives. We are living tens of years, so it's not feasible for us to just wait to our death. Let's see what we'll accomplish, and then we'll improve and learn. So it won't happen. So we need to learn based on our estimates, on our predictions of future. Okay. So where we are now? So we have we had some particular policy, some map. We evaluated it, so we know how good states are in using this policy. So we have a value function to evaluate states based on our policy. And now we just want to improve the policy, because we just evaluated it. We know how good it is. Now we want to improve it, and we do it like this. We just formulate the quality function, the state action quality function. The state action quality function just says how good it is to take this action in this state. So it's like you just take an action in this state. You see what is the reward, and then you just bootstrap everything else with your value function, with your estimates, what will happen next. And this is just what's one step look ahead. You just take an argmax on your actions. So you just choose the best action in current state, and you have new policy. And it's proved to converge to true policy, so to optimal policy. So of course we won't go through the proof, because we have no time in here. But yeah, it proved to converge. And we just interchange those two steps. We just evaluate our policy, then we improve our policy. Then we evaluate it again and improve it again. And we do it until the policy doesn't change. This is our stop condition. If we see that policy didn't change from the past iteration, we can stop. This is also improve that this is a stop condition of our algorithm. Okay. So yeah, and alpha 0 is just a general policy iteration algorithm. We will, in a minute, I will show you. I will explain alpha 0 algorithm, and we will, and we will see that this is a general policy iteration algorithm. So okay, I understand that it could be, yeah, it could be fast. So maybe some questions to this moment. Don't be shy. Okay. So yeah, so let's dive deep into alpha 0. What's the case with this algorithm? Okay, so let's remind ourselves what is this alpha 0. This is the main components are this MCTS, the Monte Carlo tree search. So we are just, because we know the rules of the game, we can just simulate what will happen if we take such actions, and we just search through the tree, so through the game tree. Then we have our policy network. The policy network tells us which actions are reasonable. So, for example, it can be some expert policy, how human experts play, and the policy just tells us those actions are good, are played by experts, and those actions are not. So you shouldn't consider those bad actions, because this is wasteful computation. And as we remember, there are so many states, and the branching factor is so high that this is really important to just dismiss those bad actions. And there is a value function, which value network that allows us to evaluate those nodes and states. So, for example, we don't need to search until the very end of the tree, until the game ends, and we see if we won or lose. We just can stop at some depth and evaluate the state with value function. And AlphaGo 0 is trained by self-play reinforcement learning. So it combines those neural networks with MCTS in elegant policy iteration framework to achieve to find the best policy, how to behave in states. Of course, there are some requirements of the problem. As I was already stating, you need to have the game. You need to know game rules. So you need to be able to search. So, but first of all, let's start with the physics. So discrete. So you need a discrete states and action. Discrete means that you have some discrete board configurations, stuff like this. So you have discrete time steps when you can that you can consider. There are also discrete actions. So those aren't continuous. Like, for example, with joint movement, I can represent movement of my joint with continuous value, but it's not the case in board games. In board games, we just have moves. So just place a stone in some positions. So yeah, the environment has to be deterministic. So every move has some one possible outcome. So it's not like you just don't know what will happen when you take some action. You just put a stone. If we consider the example of Go, with perfect information. So the perfect information means that the state that we get from the environment is like perfect information. Is everything we need to know to make a reasonable decision. So it's not like that we don't know something. That something is hidden from us. It's not like it's noisy, so it might be not true. It's just we see the board, and the board is everything you need to know about the game, about current state, the game, to make best decision we can. So, for example, in life, it's not the point. Like we aren't given with perfect information. Like for example, I don't know what do you think, and so how can I when I interact with you, I just consider what you might be thinking, and then I respond to this partial information. But in perfect information world, we would just know everything about the world, about every atom, how it moves. We would know everything that is needed to just make a perfectly informed this decision. So we are just guessing. In our lives, we are just guessing. We just guess what other people think, what other people need, because you don't have perfect information. And yeah, access to game rules. So it's like you need to know what are the rules to just simulate it. To just for example, in your mind, think what will happen if I take this action. Okay, and AlphaZero research. Yeah, and one more thing, about my research. So you don't have this. What if you don't have those game rules, like in our lives? Because, for example, human interactions are so complex that it's really hard to just write some formula that describe the interaction of humans, social interactions. So what you would like to do is just learn this model, those rules that rule the world. So this is exactly what I do with my friends. We just try to have another neural network that is just trained how particular world that it's placed in works, and then without access to game rules, it can just learn those rules and do the search exactly the same. So this is the topic of our research, and also research of many other maybe smarter people. So yeah, so I don't think that we are getting there. So don't worry. Okay, so AlphaZero research. So AlphaZero research is composed of some steps. We have the whole iteration is called simulation. We do many simulations in one planning session. So the first thing we do is select step. Select just pick when we have some game tree from previous step, because we don't throw it away every simulation. We retain it. So if we have some nodes. We have some nodes in the tree. We just move through those nodes. How we decide which action to take, we will tell later. I will tell you later. But you just go until the very end when next node isn't uncovered. So the next node wasn't seen already. So then you just uncover it. You just see what will happen if you take this action, and this is called the leaf node. So this is a leaf of our tree. And then what you do, you just expand this leaf. So you just check what your game rules tell that will happen, and you also evaluate it. So you use your two networks, policy network and value network, to just tell you what are reasonable moves from this particular state. You save it in this node for further lookup. This is those those probabilities of actions. And also you evaluated the value of this node, and you take this value. So how possible it is that you will win from this state, and you just backup it to your parents in the tree. So you just update a Q value of this action that was taken from this state. Based on this value. So it's just like averaging, that you just save, you just add up all the values that was further in the tree, and you divide it by the number of visits of this action. So then you get a quality of this action. So you back up it to root. You just you repeat the simulations as many times as you can, because the algorithm has any time property. So the estimates get better and better with each simulation. And for example, if the time finishes, you don't have more compute time. You just end planning and make a move. And you make a move based on visit counts. So in the root now you have some visits, because you choose an actions. I will get to it how we choose actions in a minute. And you have visit counts. So the point is that you will visit more better actions more often. So you just pick the action that was most most often visited. And then you do this action in the environment, and the planning starts again. You simulate once again, I don't know, 20, 100, 500, 1,000 times. You just do thousands of simulations, choose an action, make it in the environment, and plan again. Okay. Okay, so yeah, so how we choose those actions in the tree? So there is, of course, the there's of course the exploitation problem. So it's like with life. So you have your favorite restaurant, and it's around the corner, and you can go to this restaurant, and you know that you will have a good meal there. But of course, when you go to the restaurant, you exploit your knowledge, but you don't explore other options. You don't know if there, for example, there is maybe better restaurant that maybe fits you better. So this is the trade-off. You need to explore a little to know if some other options are better than what you know. But at the same time, you don't want to do like random stuff. Like you know that some stuff is some stuff is obvious that you don't like it. Like for example, you just don't eat dirt because it's awful. Yeah, I didn't try that. Okay, I tried it when I was a child, but yeah. Okay, but you exploit your knowledge. Like you know that the dirt is awful because you tried it like when you were a child. So you don't do this. You just exploit your knowledge. You know what places are reasonable, and this is the thing that we should do. And this is exactly what AlphaZero is doing. And there is next formula that I really don't want to tell exactly what does it mean, but I didn't know how to do this better. So this is utility of particular action. And utility is just a sum. This is our quality of this action because this is summed value. And this is this visit count. So you just divide sum of values that was backed up to this time by the number of visits of this action. And so this is just a Q, like quality. And then there is also this exploration term, because this is like exploitation. You just exploit your knowledge. You know that this action has this value, this quality. So you exploit your knowledge. But then there's also exploration term, and the exploration term is just number of visits of this action of all the actions divided by the number of visits of this particular action. So you can see that when you visit some action really often, this term decreases. So when you visit some action very often, the other actions get a bonus. That those are like you didn't visit them, so you should visit those other actions, because in other actions this term goes up and this term doesn't change because you don't choose them. So this is just exploration term. You just the actions that are not explored yet get some additional bonus. But at the same time, if those actions or the other actions have really bad quality, then that nothing can change. Like this bonus will not change much. And the C parameter is just a trade-off between exploration and exploitation. You can enforce the exploration. Yeah, and it gets worse because next we have okay. So, but again, we want to somehow incorporate our expert knowledge, because, like I said to you, the chess and shogi and Go have very large branching factor. In case of Go, it's very large branching factor. So you just don't want to explore every action because you don't have time for it. You just don't have compute for it. So it would be nice to have some expert policy, like for example, train from expert games or just an expert that would tell our algorithm like those actions are reasonable. You can try them. Maybe some good will come from it. And those actions are bad. You shouldn't try them because no one plays like this. For example, I'm an expert. I know that those are bad. And so what changes is just this probability. We just multiply this exploration term that we saw earlier with the probability. So probability of particular actions between, of course, 0 and 1. So we can decrease probability of exploring bad actions using this expert probability. Okay, and so how we could. So how we could, for example, get this expert? Like I said, we could just have an expert, like human plays, human games, and just train from it, just see how a human expert plays. But also this term is like an intuition, because you know in your intuition that those actions were good and those actions were bad in the past. So you just incorporate the algorithm incorporates its own experience, because it plays in the environment. It can see what is good, what is bad, and it can incorporate its knowledge to the policy network. So it just trains its policy network what actions are reasonable and which are not. And so this is the breakthrough. Like this is the idea of intuition in the computer, like in the artificial intelligence. This is this intuition part. Okay, so yeah, but of course I told you that I'm like using deep learning in reinforcement learning. So, but we didn't see any deep learning yet. So the problem is that like I told you, the Go have many states, like more states than there are atoms in the universe. So we need to generalize. Like it's not like we will visit every state and learn about every state, because we won't visit them. I think that this is like ancient game. They play it from ancient times. I don't know how long, but yeah, from ancient times, because ancient. I heard or I read somewhere that every like all the people that played the game didn't visit every state yet. And they will never, like, I think that, life on Earth will end before we will visit all the states. So this is not possible. We need to generalize. We just need to generalize between our knowledge. So generalization is like you just take knowledge from one situation, and then you generalize it to other situations. Like in life, I like, for example, with presentation case, I do a presentation, and this is like new presentation to me, but I generalize the knowledge from other presentations to this situation. So, how to model this generalization. Of course, the deep learning and deep networks are good at generalizing. So this is the power of them, of those methods. So we model the value function, a policy network and value network with deep neural networks. And yeah, who knows the guy? Yeah, this is Hinton. This is like godfather of deep learning. So he proposed the backpropagation algorithm back in previous century, and because there was no enough compute, no one was using it. So yeah, the algorithm that we just try now are with us in this world from previous century, but no one used it and couldn't use it because of hardware was too bad. Yeah, and I have a note that DeepMind used ResNet. If someone knows the architectures, so the architecture is ResNet. Okay. Of course, you can find all the details in the original paper, and I also encourage you to do it. So yeah, so we have everything. Like we have whole AlphaZero. We saw every piece, so we can just put everything together. So complete training algorithm presents itself like this. I know that you can read it, and it's good. So full infographic you can find in references to this presentation. The infographic is really good. I really recommend you looking at it and to broadly understand what the algorithm is. So yeah, so the algorithm presents itself like this. We have some randomly initialized neural networks. So there are some random weights in the neural networks. We play a couple of games. To just get an experience, what is good, what is bad, to see how environment works. At each moves, we save action visit counts. So I told you that we have in this tree, in the root, there are those visit counts. How often we visit particular state, and because of the UCT formula, upper confidence bound. After confidence tree, we know that we explored a little, but also we exploit our knowledge. So those so high visit count is reasonable to tell that this action is good. So we save those, and we'll use those action visits to improve our policy, to improve our intuition. So we have some experience that those actions are good, and we use this to train our intuition, our policy network. And then at the end of each game, we record what is the return, if we won or lose. And we just for all the experience that we or for all the states that we encountered, we just save it that like those states. From those states you can win, or from those states you can lose. And because of you just save a lot of this experience, those values average. So we train our value function to just predict what is our possibility of learning from this experience, from savings of games returns in our experience buffer. And then you just train those neural networks on data gathered. So you have this experience, you have the visit counts, you have the values, you have the winning counts, and you just train those two networks. And then you start again. You just self-play with itself. You gather more experience. You train your networks, and again. So you have this policy iteration. So this so playing is like playing and saving those values is like policy evaluation. You just see how good is your policy, current policy. And policy improvements is this saving of visit counts, because tree search is like this look ahead. That we look ahead what will happen, and we just get better policy, and we train this our intuition. You can also pit this train network with the previous one to see if it really learns. So, for example, in our implementation, we do it like this: we train a neural network, and then we check if it is better than current best. If yes, then we exchange them, and we just froze the weights of the networks, and the current network is current best. Then we play, learn. See if the one that is already freshly learned is better. If not, we leave it to learn more. Okay, and there are good reads. Of course, you can see it also, but you will have a presentation. Those bolded ones are better, like more high level. But the other ones, I also, if you want to dive really deep, those are good materials to just understand the reinforcement learning and this AlphaZero algorithm. I have that. I think that I included everything. There is also AlphaGo movie on Netflix. And I really like, so it's maybe, it's not for everyone, but it's really good. It's like, action movie of some math algorithm of some nerds from DeepMind. It's really funny to so it's shown in a really funny way. So now I have some live, because we started with some due. So but of course, they told me that you will show a camera to my that will put a camera on my screen. Sorry. Yeah, someone told me that they will come here because they couldn't connect my computer to the monitor and they will show just my screen. So okay. So questions in this. Some questions? Yeah. Yeah, of course. Yeah, of course. Also, there are. You can just visit my GitHub. There is a presentation. There is AlphaZero reimplementation. There is world models reimplementation. There is also my framework in reinforcement learning. So there is good stuff. It's like Piotr Januszewski, so Piojanu on GitHub. Okay. Sorry, there is a woman was first. Okay, sorry.
Is this algorithm like? Is it possible to adapt this to games with chance involved, like poker, for example?
Yeah, of course, yeah. Like and in poker, we also know the game rules, so yeah, it's possible. But you have the uncertainty. Yeah, you have the uncertainty. Yeah, you don't have perfect information.
That's what I am asking.
No. Yeah, the requirement is broken. You don't have a perfect information because you don't know the cards of other players. So yeah.
So if you wanted to play poker with an algorithm, you would have to write something new. Like we
you would have to adjust it in some way.
Okay. Yeah. Thanks.
Yeah, but yeah, you was next. Okay.
So what other problems you could imagine to solve with AlphaZero? We spoke about games.
I understand. Yeah. So where it is used, because it's everything nice, but where is the practical usage? So yeah, Google, for example, they use it to optimize their energy usage. of their data centers, and they told, I don't remember numbers right now, but there it's like 20% improvement on energy usage in data centers. There's about the cooling. So for example, they use it this way. I also because my research is like to adapt this method to environments where you don't have these game rules. So for example, I imagine that I would like to, for example, somehow adjust it to problem of insurance, so uncertainty, like considerations of what could happen and stuff like this. But this is just an idea, and Google used it like this is true usage case.
Okay, and can you implement it for smaller scale problems?
So, yeah.
We spoke about Google, but let's imagine not everyone has.
So there is always this problem, you know. I think that for now I don't have like more ideas you could use it in everywhere that you just incorporate some search. You can train some model. If my research will do good, you will be able to train some model and just to search through possible outcomes and choose some and just decide on your action. So every time you have some problem that is there are just actions that are somehow correlated to each other, and you have just trajectories, the series of states, that then you can just fit somehow the reinforcement learning framework. And also there are of course many methods to solve those kinds of problems, reinforcement learning problems. This is one of them. But I also agree that deep reinforcement learning is like it doesn't really work yet. There is a good post, you can find it in Google. Deep reinforcement learning doesn't really work yet, and this is really good post that tells you that this is a critical view on deep reinforcement learning, because there is a lot of this is a really hot topic, right? So yeah, everyone wants to do this, but this is like just research phase. So there are, like, deep reinforcement learning isn't just practical yet. I don't think that is used somewhere. If for example, you know the Boston Dynamics, like they do those robots. Many people think that they use reinforcement learning, but they don't. They use more traditional methods. They don't use reinforcement learning because reinforcement learning methods aren't like grown enough yet. Okay.
So, if I remember correctly, the standard size of the Go board is 18 on 18.
19 on 19. I think. Yeah,
maybe.
Okay.
Would it really matter if we change the size to, I don't know, 32 on 32, or this algorithm will still win with the grandmaster?
Yeah, of course I don't have data, so I can't tell you if it would, because But I think if it won in 19 by 19, and then you just scale it to 32 by 32, then humans also have to have like bigger, like more states. So I think that it will exceed, maybe even better, maybe even more human. But yeah, for example, I trained it for other games, for Othello and Connect 4, and it's like smaller network, because of course I don't have 5,000 CPUs to reproduce their work. So I trained it for Connect 4 and Othello, and also for tic-tac-toe. I would like to show you tic-tac-toe, but because tic-tac-toe learns like in 1 minute, so yeah, but I can't. But the code is in the internet. So yeah, so I trained it for smaller ones, and then I tried it on some friends that know how to play those games, and AlphaZero won with them. And I was training it like for 1 week in uni on 1060, GeForce 1060. Okay.
One more question. So I wonder if we could use this algorithm in the code programming.
Yeah. So yeah, there is other work on deep learning to train machines to code. And even there is work to so neural networks just come up with other neural networks architectures, but this is not. I don't think that this is a usage case for this.
Okay, so my question is, could we use this AlphaZero algorithm, to write a boat for this code tournament, which is ongoing? And it's part of the conference.
So to be clear, you ask if AlphaZero could write a code.
Not code, but if we could create a bot
Bot,
with
yeah.
AlphaZero algorithm
Mhm.
inside it to win this code competition.
But I don't know what is about the competition, so
Okay.
yeah. I don't know what is the problem, so I don't know. So yeah, so the requirement is broken, like this says, yeah. I believe you. Okay, more questions? So yeah, so I will be in here for like more 20 minutes more, so we can talk offline. So yeah, thank you for being in here with me.